Next is the half-wave rectifiers. In this topic, we are going to cover the basic DC power supply, the half-wave rectifiers itself. We are going to learn about the effect of the barrier potential on the half-wave rectifier output and the half-wave rectifier with transformer coupled input voltage. So the basic of DC power supply is that we know that the DC power supply are going to convert the standard 110 volt, or in Malaysia we use 220 to 240 volt, of a frequency 60 Hz of alternate current AC available at all wall outlets into a constant DC voltage. So that is a DC power supply. So it's going to convert any AC voltage from the outlet into constant DC. And then we have a rectifier. Okay, we have a rectifier that converts the AC input voltage to a pulsating DC voltage, and we are going to obtain a half wave rectified voltage. Okay, only the positive alternation uh, is being allowed to flow through this rectifier. And then if we look here in the figure B here, this is going to be the complete power supply, which include a rectifier, a filter, and regulator. Okay, so basically the rectifier, the AC currents are going to flow into the rectifier, and we are going to have the half wave rectified. And then we have the filter. So this is an example of a filtered voltage. So basically we have a capacitor inside the filter, and then we have a regulator. Okay, the filter, basically the function of the filter is to eliminate the fluctuation in the rectified voltage from the rectifier, and it's also going to produces a relatively smooth DC voltage. Okay, almost smooth but not that smooth, we still have that ripple. And then we have the regulator, which the function is uh, as a circuit that maintains a constant DC voltage for variation in the integrated circuits. Okay, so half wave rectifier. So when a diode is connected to an AC source and to a load resistor RL, a half wave rectifier is formed. Okay, so we have during if we look at the input is sinusoidal AC. When the sinusoidal input voltage V in is in positive alternation, the diode is going to be forward biased, and it's going to conduct currents through the load resistor as shown in this figure. Okay, we are going to have the output voltage. The current produces an output voltage across the load RL, which has the same shape as the positive half of the input voltage. Okay, but when the input voltage goes into the negative alteration, let's say from T1 to T2, which is the second half of its cycle, okay, the diode are going to be reverse biased. Okay, it's going to be reverse biased, and therefore no current are going to flow through this diode, and the voltage across the load resistor are going to be zero. Okay, it will be zero. So the output voltage are going to be equal to zero from time t1 to t2. So the last image here showed a 60 Hz half wave output voltage for 3 input cycle. So we have the first input, the second input, and then the third input. So only the positive alteration is being shown in the output voltage. So since the output does not change polarity, so it is a pulsating DC voltage with a frequency of 60 Hz. So basically this is a DC voltage, but it pulsates only at positive part, and the frequency is at 60 Hz. Next, what is the average value of the half wave output voltage? So we have a half wave rectifier and we got the output voltage which only have the positive alternation. So the average value of the half wave output voltage can be calculated using this equation where V average is equal to the peak voltage Vp, okay, divided by pi. Okay, so we are going to obtain the V average, okay, which is around 30% from the peak voltage. So let's take a look at one example. So we have an half wave rectified output voltage as shown in this figure. So if you look at the figure, we are going to see that the peak voltage for this circuit is at 50 volt. So it's at 50 volt. So what is the average value? So easily we can use the equation that we had learned from the previous part. So V average are going to be the peak voltage divided by pi. So the peak voltage is 50 volt divided by pi 3.14, and we are going to get 15.9 volt. So we are going to notice that 15.9 volt over 50 times 100 is approximately at 31.8%. Okay, so we can say that V average is equal to 31.8% of the VP. Okay. So the effect of the barrier potential on the half wave rectifier output. So during the positive half cycle, okay, the first part, the input voltage, okay, the input voltage must overcome the barrier potential before the diode become forward bias. So there will be a barrier potential that we have discussed previously, which is the offset voltage, which value around 0.6 to 0.7 volt for silicon. So this result in a half wave output with a peak value that is 0.7 volt less than the peak value of the input as shown in the next figure. So the expression for the peak output voltage is given by Vp. P is for peak output. Okay, the peak output voltage is equal to the peak input voltage minus 0.7 volt. So this is an example of the circuit. So at a positive alternation, so it must exceed the value of 0.7 volt in order to cross, okay, the depletion region in that diode, and therefore we are going to get the peak output voltage is equal to the peak input voltage minus 0.7 volt. So this is 0.7 volt less than the peak input voltage. Now let's see. Let's say we have input voltage with a peak value of 5 volt. Okay. We need to draw the output voltage of each rectifier for the indicated input voltage, as shown in this figure. So we have the first one is a diode 1N4001 and the second one is 1N4003. Okay, the load resistor is the same, 1 kilo ohm, 1 kilo ohm. Okay, the peak voltage for the first part is 5 volt. Okay, the second circuit is 100 volt. Okay, so the peak output voltage for the first circuit are going to be peak output voltage equal to the peak input voltage, which is 5 volt minus 0.7. So we are going to get the peak output voltage is 4.3 volt. While for the circuit B, Okay, easily 100 volt minus 0.7, we are going to get 99.3 volt. So the diagram are going to be shown like this. Okay, we have the positive alternation only, and the peak value will be 4.3 for circuit A, and for circuit B, the peak output voltage value would be 99.3. Okay. So some discussion on the result. Okay, you can see that in circuit A, okay, the difference between the peak output voltage 4.3 and the peak input voltage is around 14%. Okay, the difference is quite big. But for circuit B, where the peak input voltage is very high, 100 volt, okay, the peak output voltage is 99.3. So the error is significantly very small, which is 0.7%, and therefore it could have been neglected. Okay, for this kind of circuit that have a very high value of peak input voltage. Okay, next we are going to take a look at the half-wave rectifier with transformer coupled input voltage. So we have half-wave rectifier combined with transformer. Okay, so a transformer is often used to couple the AC input voltage from the source to the rectifier. So basically we are going to have the AC input voltage, and then we have the transformer, and then we have the rectifier. So the transformer coupling provides two advantages. Okay, there will be some reason why we do this, why we put transformer in between the AC input voltage and the rectifier. The first reason is because we want to step down the source voltage as needed. Okay, we want to make sure that the voltage is low. And then the second reason is to electrically isolate the AC source from the rectifier. So this is going to prevent short hazard in the secondary circuit where we have the rectifier. Okay, so we isolate the AC source from the second circuit. So the primary circuit is the AC source. The secondary circuit is where we have the rectifier. So this is the example of a transformer coupled with the rectifier and AC input voltage. So we have in the primary part, okay, in this part we have so in this part, in the primary part, we have the AC input voltage with the primary coil, and then in the secondary circuit, we have the secondary coil and the rectifier. So basically we are going to isolate AC with AC input voltage, AC input with the rectifier itself. So as we know that the secondary voltage of a transformer is equal to V secondary equal to N V primary. So this equation comes from the one that we have learned in previous topic, where N, the turns of ratio, is equal to V secondary over V primary. And we know that if the N value is larger than 1, so the secondary voltage is greater than the primary voltage, meaning that it is a step up transformer. And if N is smaller than 1, then it is a step down. Step up, step down. So we are going to define that the turns ratio N of the secondary turns, N secondary to the primary turns and primary, okay, N equal to N secondary and primary. So this is the same with the voltage. And then if we have N is equal to 1, then V secondary is equal to V primary. Okay, so that means that the voltage is same. The peak secondary voltage Vp secondary in a transformer coupled half-wave rectifier is the same as peak input voltage in the previous equation. So we have the peak output voltage, okay, in the secondary part, okay, is equal to V peak secondary voltage of the transformer minus 0.7. So the one that changed is that so from the previous equation, the Vp out is equal to Vp in minus 0.7 volt. So basically this is the same. Okay. Okay, so let's take a look at one example. So determine the peak value of the output voltage. So the question asks to find the peak value of the output voltage, meaning that we need to find the V, P out. In the figure below, if the turns ratio is 0.5, okay, 0.5. So this is the value of N, okay, which is N secondary over N primary, or V secondary, V primary. So we have the input voltage, which have a peak voltage of 156 volt. So this is going to the Vp in. Okay, and we need to find the Vp out. So the solution. Okay. So let's start by calculating by identifying the value that we already have. So we have the V peak of the primary circuit is equal to the Vp in, equal to the peak input voltage, which is equal to 156 volt. Okay, and then we need to find the peak secondary voltage, okay, which is denoted by Vp secondary, and this is going to be the value that we can obtain using the turns ratio Vp primary, and N is 0.5 and Vp primary is 156. Therefore we are going to get the peak secondary voltage is 78 volt, okay, half from the primary peak voltage. And then we need to find the rectified peak output voltage, okay, which is given by Vp out, okay, peak output voltage which have been rectified must be equal to Vp secondary minus 0.7, okay, the offset. So we are going to get 78 volt minus 0.7 volt, and the answer will be 77.3 volt. And we know that Vp second is the Vp input for the rectifier. Okay. And this is going to be our answer, 77.3. Next, we are going to take a look at full wave rectifiers. Okay, there will be two kind of full wave rectifier: the center tap and the bridge full wave rectifier. So full wave rectifiers allows a unidirectional or one-way current through the load during the entire 360 degrees of the input cycle. So we have one input cycle is from one cycle. Okay, this is one cycle. So it's going to allow only one-way current, okay, through this one cycle or 360 degrees. The result of full wave rectification is an output voltage with a frequency twice that pulsates every half cycle of the input. So you can see that the frequency here is twice than the half of the cycle in the input. So this is the full wave rectifier characteristic. The number of positive alternation that make up the full wave rectified voltage is twice that of the half wave voltage for the same time interval. So it will be twice. And therefore, the average value for a full wave rectified sinusoidal voltage are going to be twice that of the half wave. So the equation are going to be V average equal to 2 peak voltage over pi. Okay, so we have twice from the half wave rectified. And basically, we are going to have the average value for the rectified output voltage approximately 63.7% from the peak voltage for a full wave rectified. So let's take a look at one example that we have here. So find the average value of the full wave rectified voltage in the figure. So we need to find the V average. Okay, so the solution, easily we can find the V average is equal to 2 peak voltage, the input peak voltage over pi. So we have 2 times 15. So what is the peak voltage? It's going to be 15 volt over pi 9.55 volt. Okay, and then we have a center tap full wave rectifier. So a center tap rectifier is a type of full wave rectifier that uses two diodes connected to the secondary of a center tap transformer. So we have a transformer and it is being center tapped. Okay, center tap, then it's being divided into two different circuits. Okay, one connected to diode D1, the other one connected to diode D2. So let's take a look at the circuit closely. So the input voltage is coupled through the transformer to the center tap secondary. Okay, so the input voltage is coupled with the transformer. And then half of the total secondary voltage appears between the center tap and each end of the secondary windings. For a positive half cycle of the input voltage, so now let's take a look at the positive half cycle. The polarities of the secondary voltage are as shown in this figure. So we have the polarities is plus, minus. Okay, but for the diode D2, it will be negative plus. So it will not flow into D2, but it's going to flow to D1 because on the diode 1 is forward bias. Diode 2 is reverse bias. So it's going to flow. Okay, with the output is half, okay, half from the secondary voltage of the transformer. Okay, half from the secondary voltage of the transformer. So the current path is going to be through D1 and then it's going to flow to the load resistor. Next, let's take a look when we proceed to the next half cycle, the negative part. Okay, for a negative half cycle of the input voltage, the voltage polarities on the secondary are as shown here. So this time D1 are going to be reverse bias and D2 are going to be forward bias. Therefore, the current are going to flow through D2 to the load resistor. And because the output current during both the positive and negative portion of the input cycle is the same direction through the load, okay, the output voltage developed across the load resistor is a full wave rectified DC voltage. So through the load resistor here, okay, the output voltage are going to be a full wave rectified. Okay, it's going to be all positive, okay, unidirectional. So now let's take a look at the effect of turns ratio on the output voltage for a center tap transformer. So if the transformer turns ratio is 1, okay, means the primary voltage is equal to the secondary voltage. The peak value of the rectified output voltage are going to be equals half the peak value of the primary input voltage less the barrier potential, which is 0.7 volt. So we have the peak primary voltage, okay, here with a turn ratio 1. So peak primary voltage are going to be equal to the peak secondary voltage. So we can replace divided by 2. Okay, divided by 2 it will be half. And therefore, okay, the output voltage, the peak output voltage are going to be the peak primary voltage divided by 2 minus 0.7 volt. So this is one important part. Okay. Half of the primary voltage appears across each half of the secondary windings. So we know that from here, the secondary peak voltage is equal to the primary peak voltage. In order to obtain an output voltage with a peak equal to the input peak less the diode drop, 0.7 volt, a step-up transformer with a turns ratio of N equal to 2 must be used. So in this case, the total secondary voltage is twice the primary voltage, okay, 2V primary. So the voltage across each half of the secondary is equal to the V primary. So in order to get the same output voltage with the input voltage, okay, or with the primary voltage, we need to change the turns ratio into N equal to 2. So what we are going to have is this kind of circuit. The turns ratio now is become N equal to 2. Okay. VP, the primary peak voltage, okay, are going to be through this transformer, and we are going to get that similarly to the equation previously. We are going to get the VP secondary are going to be equal to 2 okay, this part here come from 2 VP primary divided by 2. Okay, both should be divided by 2, therefore we get VP primary. Similarly for the second diode also we have VP primary. So the value of the peak voltage of the secondary part are going to be equal to the primary part, and therefore we are going to get the output voltage are going to be almost similar to the input voltage VP primary, except that we have to minus the potential or the offset voltage of 0.7 volt. In any case, okay, the output voltage of a center tap full wave rectifier is always 1/2 of the total secondary voltage less the diode drop. no matter what the turns ratio. So this is the equation that are going to be used for a center tap full wave rectifier. V secondary divided by 2 minus 0.7 volt. Okay, so that's it. Next we have a bridge, the bridge full wave rectifier. The bridge rectifier used four diodes connected as shown in this figure. So we have diode D1, D2, D3 and D4 connected. So this is the circuit that shows the current flow during the positive half cycle of the input. So when the input cycle is positive, okay, in this part, okay, diodes D1 and D2, only diode D1 and D2 are going to be forward bias, while D3 and D4 are going to be reverse bias. And therefore the currents are going to flow through D1 and D2, and the voltage are going to be developed across load resistor RL, and it's going to look like the positive half of the input cycle. Okay. So sama, dia akan sama macam input. And during this time, D3 and D4 is reverse bias, so no current is flowing. Then during the negative part, okay, during the negative part of the half cycle input voltage, diode D3 and D4 are going to be forward bias, but D1 and D2 are going to be reverse bias. Okay, currents are going to flow through D3 and D4, and it will go to load resistor and produce uh, an output voltage with a negative with a positive value. Okay, basically it's going to be opposite to the input voltage. Okay, because the current flow here is all in one direction. So a full wave rectified output voltage appears across RL as a result of this action. During the positive, okay, the output voltage also positive. During the negative, in the input voltage, the output voltage are still positive. So bridge output voltage during the positive half cycle of the total secondary voltage, diodes D1 and D2 are forward bias. And then if we neglect the diode drop 0.7 volt, the secondary voltage appears across the load resistor. And the same is true when D3 and D4 is forward bias during the negative half cycle. So it's going to have the same effect. So ideally, we are going to have this kind of circuit where the primary voltage, okay, cross through the transformer. We are going to obtain the secondary voltage, and we have the bridge full wave rectifier, and basically we are going to get the peak output voltage is equal to the peak secondary voltage. Okay, but the practical diodes, okay, considering the diode drops, okay, what we have is that two diodes, okay, with two offset voltage 0.7 volt, 0.7 volt, meaning we have double of the offset voltage. The peak output voltage are going to be less than the peak secondary voltage. And how much less? We have two diodes, meaning that it's going to be less 1.4 volt. Okay, 1.4 volt. So two diodes are always in series with the load resistor during both positive and the negative half cycle. So if we take account the diode drops, so the output voltage are going to be VP out, peak output voltage, equal to the peak secondary voltage minus 1.4 volt. Power supply filters and regulators. So next we are going to learn a little bit on the filters and regulator. So basically, a filter, a power supply filter, will ideally eliminate the fluctuation in the output voltage of a half wave or a full wave rectifier, and in the end, it's going to produce a constant level DC voltage. And then we have filtering. Process is necessary because the electronic circuits require a constant source of DC voltage and current to provide power and biasing for proper operation. So some electrical equipment must use DC voltage, a constant source of DC voltage in order to operate. So filters are implemented with capacitors. Voltage regulation in power supplies is usually done with the integrated circuit voltage regulator. So a voltage regulator prevents changes in the filtered DC voltage due to the variation in input voltage or load. So a rectifier without a filter, we are going to obtain uh, this full wave rectifier output voltage. Okay, but with the filter, okay, which include a capacitor, the output voltage are going to be much more constant or much more smoother. Okay, so we still have the zigzag, the ripple. Okay, so we are going to solve this problem in using the regulator afterward. Capacitor input filter. So a half wave rectifier with a capacitor input filter is shown in the figure next. So we have this figure. So we have a diode, we have a capacitor, and we have a load resistor. The input voltage is AC. Okay. What happened is that this is going to be a filter which consists of simply a capacitor. Sorry, the capacitor connected to the diode, which act as a rectifier output, and to the ground. Quarter cycle of the input. Okay, we are going to look at quarter, not half, like the previous part. We have the quarter now because we have capacitor. The diode is going to be forward bias. Okay, so it's going to flow. The current are going to flow in this direction, and the capacitor are going to charge within the 0.7 volt of the input peak. Okay, so it's going to charge. Okay, VC are going to be input peak voltage minus 0.7. Then when the input begins to decrease below its peak, the capacitor retains its charge and the diode become reverse bias. So now diode become reverse bias, currents will not flow through the diode anymore, and the discharging are going to occur during the portion of the input voltage indicated by this solid blue curve. So in this part, capacitor are going to discharge. So during the remaining part of the cycle, the capacitor can discharge only through the load resistance at a rate determined by RLC time constant, and this is normally long compared to the period of the input. The larger the time constant, the less the capacitor will discharge. Okay, then what we have is we have a new cycle. Okay, then during the first quarter of the next cycle, okay, the diode will again become forward bias. Okay, again it will become forward bias and it will charge the capacitor again when the input voltage exceed the capacitor voltage by approximately 0.7 volt. Okay, so the output voltage are going to be like this. Okay, this is when the discharge happen, and this is when the diode is forward bias again. okay, and capacitor is being charged, and this is going to be repeated for next cycle. So the shape that we've found here, okay, is a shape that consists of ripples. So ripple voltage, okay, is the terms that we use uh, to represent the variation in the capacitor voltage due to charging and discharging. So charging, discharging. So this is the part where it's charged and then discharged, charged and discharged. So the variation in this value of the voltage is called as the ripple voltage. So generally ripple is unwanted. Okay, therefore smaller the ripple, the better the filtering action. Okay, uh, the best is that we have no ripples. So larger ripples means less effective filtering. So we have larger ripples. This is very large from the peak to here. Okay, smaller ripples means more effective filtering. So generally, the larger the capacitor value, the smaller the ripple for same input and load. Okay, so if we use larger capacitor, or if we use larger load resistor, then the ripple effects or the ripple voltage are going to be much more smaller. So let's take a look at different. So for a given input frequency, the output frequency of a full wave rectifier is twice than of the half wave rectifier. And this is going to make the full wave rectifier easier to filter because the time between the peaks is going to be much shorter. So if you look at half wave rectifier with the same frequency, okay, half wave rectifier, the peak is here, and then the next peak is here. So the ripple effect, the ripple voltage are going to be very large. Okay, although the slope is the same with the full wave rectifier. Okay, the slope is the same. Basically, the slope represent the discharge rate of the capacitor. So when filtered, the full wave rectified voltage are going to have a smaller ripple voltage than the half wave rectifier. So it means that it will be better to use full wave rectifier in order to obtain a constant DC voltage. The capacitor discharge less during the shorter interval between full wave pulses. Okay, that's why the ripples are going to be very small. So ripple factor. Ripple factor or R is an indication of the effectiveness of the filter, and it is defined by this equation. R equal to VRPP. So we have a lot of symbol that we learn in this topic. So VRPP is the peak to peak ripple voltage, okay, over VDC. So VDC is the direct current average value of the filter's output voltage. So the average value. So the lower the ripple factor, the better the filter. So the ripple factor can be lowered by increasing the value of the filter capacitor or by increasing the load resistance. So we have rectified peak voltage, okay, and then we have the DC VDC, the average value of the filter's output voltage, okay, is the average value here. Okay, then we have the peak to peak ripple voltage, okay, from here to here, okay, from this point to this point. For a full wave rectifier with a capacitor input filter, approximation for the peak to peak ripple voltage VRPP and the DC value of the output voltage VDC is given in this equation. So we have VRPP, peak to peak ripple voltage is approximately equal to 1 over frequency times the load resistor times the capacitor times the peak rectified voltage, okay, approximate. While the average DC of the filter output voltage is approximately equal to 1 minus 1 over 2 FRLC VP rectified. Okay, so VP rectified is the unfiltered peak rectified voltage. So unfiltered peak rectified voltage, which is this part. Okay, this part. So let's take a look at one example before we finish this topic. Determine the ripple factor for the filtered bridge rectifier with a load as indicated in this figure. So we have 115 volt RMS with a frequency of 60 Hertz, and then we have the peak primary voltage, peak secondary voltage. The turns ratio is 10 to 1. Okay, means that the secondary voltage are smaller than the primary voltage. And then we have a bridge D1, D2, D3, D4. We have capacitor with 50 microfarad, and the load resistor is 2.2 kilo ohm. So we need to find the ripple factor. So first what we need to do is to calculate the turns ratio N, which is 1 over 10, 0.1, and we can find the peak primary voltage, okay, VP primary is equal to 1.414 VRMS. So this is going to be equal to V 1.414 times 115 volt, and we are going to get 163 volt. Okay, and then the peak secondary voltage, VP secondary, are going to be the turns ratio N times the VP primary. We know N is 0.1 and VP primary is 163 volt. So we are going to get the peak secondary voltage is only 16.3 volt. And then the unfiltered peak of a full wave rectified voltage, which is the VP rectified, are going to be equal to VP secondary minus, we have two diode in the bridge, so minus 1.4 volt. So I'm going to write the answer 14.9 volt. Okay, 16.3 minus 1.4 volt. Okay, so the frequency F is equal to 120 Hertz. Okay, we obtain this from which is double, okay, 2 times 60 Hertz from the input frequency. Okay, the approximate peak to peak ripple voltage at the output is, okay, so how to write peak to peak ripple voltage or VRPP is equal to is approximately equal to 1 over F RLC times VP rectified. Okay, so we can substitute the value 120 Hertz, and then RL is 2.2 kilo ohm, capacitance is 50 microfarad, times the rectified peak voltage 14.9 volt, and we should get the peak to peak ripple voltage is 1.13 volt. And then we need to find the DC voltage, the approximate value of DC voltage, VDC, using this equation, 1 minus 1 over 2F RLC VP rectified. Okay, and we can substitute the value, and we should get the answer is 14.3 volt. So the ripple factor or R are going to be VRPP over VDC, which is 1.13 over 14.3 is 0.079. So the percentage, if we can write the percentage of the ripple is 7.9%. Okay, so that's it for diode. Okay, see you again for the next topic. Assalamualaikum warahmatullahi wabarakatuh.